Hello, welcome back to this series on trigonometry with college algebra. This video is a continuation on what we started when we were talking about relations and functions. We're going to dive a little bit deeper into that and talk about domains and ranges here. So without further hesitation, we'll get into it. So we're going to talk about finding the domain and the range when it's defined by an equation. In the last video, we kind of started with maybe the domain and the range and could just see the direct relationship here, but we'll often describe functions by an equation, and we'll need to think about what the domains and the ranges might look like depending on that equation. We'll want to be able to find a domain and range from a graph of a function, and then we'll talk about sketching piecewise functions at the end here. So finding domain and range by an equation. The domain of a function defined by an equation is all of the values that can be plugged into the equation without quote unquote something going wrong. It's kind of an informal way to think about it, and maybe a backwards way, because really we're trying to find all the values that we are allowed to plug in. But often that's an infinite number of values, and it's very hard to write down an infinite number of values. So it might be easier to think about, okay, what values would I not be able to plug into this equation? Like what values, if I plug them in, something would go wrong? And there's always kind of a handful of situations where something could go wrong, and we'll see a few on this page. But it's like, am I going to divide by 0? That would be bad. We all know in math, the world blows up, of course, if you divide by 0. So we don't want to do that. We don't want to take the square root or the fourth root or any even root of a negative number. So we need to make sure that our domain leads to a non-negative radicand. And then we also want to make sure that we don't take the logarithm of a non-positive number. So there's no example on this page. We will talk about exponentials and logarithms later on. So when we get there, we can talk more specifically about those domains. But the idea for these examples here is we want to think, okay, is there any number, if I plugged it into this equation, if I plugged it into this function, would cause something bad to happen? So let's go through these. I didn't mention the range. The range is all of the output values from the domain being plugged into the equation. So that's a little bit weirder to find, and we won't do that so much in our homework for my class. For the most part, unless it's kind of easy to see in this first example, it might be easier to see what the range is. But the range is, once we plug in all of those domain values, what are all of the output values? So in this first example here, and I did have to put in this little caveat that we're looking for real number valued domains. So we could think maybe about complex numbers in terms of our domains and ranges and stuff, but we want to make sure that everything stays real valued here. I know we have complex numbers and we can use those, but for right now we're just thinking about real numbers. So in this first example here, I'm thinking, okay, I've got this function f of x, which says square the input and then subtract 1. Now I'm thinking, is there any number, if I did that, something would go wrong? Am I going to divide by 0? Am I going to take the root of a negative number, the even root of a negative number? Am I going to take the log of a non-positive number? No, everything's okay here, right? Like, just think about examples of numbers you could plug in. 0 is fine. 0 squared is 0. Subtract 1 is negative 1. That's totally fine. We get a result from that. So there is no danger here. This is a very all-inclusive function. It's letting everybody come to the party. So the domain in this case is all real numbers, and we can represent that in interval notation by saying that's going from positive infinity to negative infinity. And we'll use, of course, the parentheses on the endpoints here, because infinity isn't a number, it's just a direction that we can walk. We can either walk in the infinite direction forever or the positive direction for forever. I don't know if my video is mirrored here or not. Hopefully I'm pointing the right way. But we can never attain those values. So what I'm getting at is sometimes we would use these brackets on the end to indicate that there is inclusion of the endpoints. But we cannot include infinity or positive infinity. So our domain here is open parentheses from negative infinity to positive infinity. And then thinking about the range, all of the values that would come out of this, well, we would get, and this is a little less clear, and this gets talked about a little bit more in higher classes and more advanced math classes is what I mean by that. But the range here would also be from negative infinity to positive infinity. We would hit all of the numbers once we plug in all of the numbers. So this one, fairly straightforward. Hopefully you are convinced that there's no weirdness going on here. We're allowed to plug in any number that we want, and we will get another number out the other side. For the second example here, now there's a little bit more to think about. We have a fraction here, which means that there is a denominator, which means, and there is a variable in the denominator, which means that there is a chance that we might end up dividing by 0. So we want to make sure that that does not happen. So here, what I'm thinking about, and this is just kind of maybe my scratch off to the side, what we're trying to find is all the numbers we're allowed to plug in. Well, an easier thing to do is to think about all the numbers that would be bad to plug in, and hopefully, you would be convinced that and I'm just focusing on the denominator here, that x plus 2 cannot be equal to 0. If x plus 2 was equal to 0, then we'd be dividing by 0, and that would be bad. So in your head, you could probably already think what number that would be, but setting it up in this very, very direct way by setting up this, inequality, or not inequality, but non-equality, that x plus 2 can't be equal to 0 means that we can then subtract 2 from both sides, and we would get that x cannot be equal to positive 2. And I think that, negative 2. X cannot be equal to negative 2. Because if we plugged in negative 2 here, then we would end up dividing by 0, and that would be bad. So the way that we would write the domain here would be, well, let me maybe create a little bit of space. Oops, wrong tool there. And I'll scoot this guy over. So if I'm looking for the domain, well, any number from negative infinity up to negative 2 is going to be totally fine. All those numbers we can plug in. But let me not include negative 2. So I'm going to put an open parenthesis on that negative 2 to indicate that we are not including negative 2 in our domain. And then anything starting on the other side of negative 2 is also going to be okay, up to positive infinity. So right now we've got these two separate intervals that are both parts of our domain, and we will join them together with this union symbol. So it looks like a U, and it probably looks that way because it stands for a union. We also have this intersection symbol, which means that we're looking for where these things overlap. But here I'm just trying to glue these two kind of subdomains together to make a full domain. So what this is saying is any number from negative infinity to negative 2, totally legit. We can plug those in, skip over negative 2 though, and then pick it back up at right past negative 2 all the way to positive infinity. So kind of a weird thing there, but that is how we represent our domains in interval notation when we just need to pluck one value out. We just separate the domain into all of its intervals and glue them together with this union symbol. All right. For this next example, we have a square root here, and we are trying to make sure that we can take the square root without getting some sort of complex number. We want to make sure that everything stays real valued here. So what would be bad in this case would be to take the square root of a negative number. So if I wanted to write that in a mathier way, I could say, well, I need 2x minus 3 to be bigger than or equal to 0. So what this is saying is that I need that radicand, I need that 2x minus 3 to stay positive or 0. It could be 0. We can take the square root of 0. It is just 0. But it needs to be non-negative. So I can do a little quick algebra here. I can add 3 to both sides. This says that 2x must be bigger than or equal to 3. I can divide both sides by 2. And this says that x needs to be bigger than or equal to 3/2. So this is what I'm going to use to write my domain. So what this is saying is that I need to find all of the numbers that are bigger than or equal to 3/2. So I'll start with the square bracket here, which says, yeah, 3/2 is totally valid, totally legit. We could plug in 3/2 to our original function here, and we would get 0 out the other side, and that works. And then any number bigger than that will also work. So that will just go to positive infinity. So this is our domain in this case here. So anything from 3/2 inclusive to positive infinity, we are allowed to plug into this function and not get any sort of weirdness to happen. We won't end up getting a complex number or anything like that. I've ignored the ranges on these next two examples because, like I said, there's a little bit more to think about that, with maybe some holes in the graph or part of the graph not being included. Or I shouldn't even say that because it's not part of the domain. But that'll be something that we can explore in future classes. For right now, we're kind of just thinking about the domains, unless we're in the situation where the range is also the same as the domain. We just get all real numbers, which is a little bit easier to see than some of these weirder examples. Right, in this next example here, we're going to look at finding the domain and range from a graph. So again, the domain refers to the set of possible input values, and that corresponds to the horizontal x-axis here. So we can reference this this x-axis to see, okay, what values in our domain are being sent to output values. And you can see, like, oh, where's this go? Like that didn't have anywhere to go over there. So there's something to think about in this example here. And then the range is the set of all the possible output values, which are shown on the y-axis here. So again, we can think, okay, just kind of map stuff back. Well, that's not where I was looking, but we can, find, okay, there are some output values here that are going, oh, but like up here, where did that come from? There's nothing up there. So there's some stuff to think about. So looking at this example here, if I'm looking for all of my input values, we can see, as I kind of alluded to before, maybe I'll change my colors. This blue is not that satisfying here since there's already blue on the page, or in this picture. But kind of like I said, like if I tried to figure out, okay, where would -6 go? There's no part of this graph that it's being mapped to, which means that -6 is not part of our domain. Okay, so where does our domain start? Well, where does our graph start when we're moving from left to right? That's where all of our input values are. And -5 is where our domain is starting. And then I'm just thinking, okay, now as I move across the graph here, is there any other spots where there's not part of this graph? And as we're moving across from left to right, there are values everywhere. And what this is saying with the arrow at the bottom is that this just continues down, and even though it's going down very sharply, as we continue to move in the positive direction, all of those values will continue to be hit. So if I'm looking at my domain here, what this is saying is, and since this is a closed circle that we started with, this says that -5 is part of our domain, but nothing smaller than that. So we are using that closed bracket, that closed square bracket, to say, okay, -5 is where we're going to start with our domain, and that is allowed. And then any number bigger than that is also part of our domain. And we're going to use that open parenthesis on the infinity side because, again, that's just a direction to walk. It's not a number we could ever attain, so we need to use the open parenthesis there. All right, and now looking at the range. Here, instead of kind of looking at the x-axis and moving left to right, here we'll look at the y-axis and we'll think about moving up and down. So, depending on what the graph looks like, you might look for a largest value or a smallest value, or where, it could be that it's all values as well. But here we can see again that this one starts up at +5. So we're looking at the y-axis now. And as I move down, well, it's hitting all of these values moving down. Oh, it's moving back up a little bit here. So I can tell now that this is not a one-to-one function, because there are some output values that are being hit by multiple inputs, and that's okay. That's still a function. And then it turns back around, and now it's heading back down again, forever down that way. So if I'm looking at my range, I'm just looking at which parts of the y-axis are being hit or being kind of mapped to part of the graph here. And that is starting, here the largest value is 5, so that is actually going to be, now I need to undo a little bit here because I wasn't thinking ahead, but the largest value here is going to be 5, because that's the largest value here, and then everything down to -infinity is going to be part of the range as well. So this is, I'm writing it backwards to the way that I thought about it, but when we're writing stuff in interval notation, we always need to be putting the smallest number, or the smallest, I don't know, because negative infinity isn't a number, but we need to start with the smallest values, even if that we consider that negative infinity, and then the largest value goes in the second space here. So the range here is from negative infinity all the way up to positive 5. So we're just getting that from the graph here. All right, and the last thing that we're going to do is we're going to sketch this piecewise function. So in a previous video, we saw piecewise functions and how to define them. That example had 2 different sub-functions as part of how it was defined. Here we have 3 different sub-functions for how this one is defined. Just kind of investigating what this is saying is that, okay, for any x value that is smaller than or equal to 1, we're going to use the squaring function. So this is kind of the most basic quadratic function. Take your input and square it. If we are in between 1 and positive 2, so positive 1 and positive 2, and including positive 2, then we just get this constant function of 3. No matter what the input is, the output will always be 3 if we're between 1 and 2. And then for any number bigger than 2, we just get the identity function. So it's just saying whatever the input is, the output's exactly the same. And depending on which part of the domain we're looking at, we'll get a different one of these sub-functions. So we're just going to graph kind of all of these together here. Thinking technology-wise, what's going to work here in terms of graphing this, because sometimes it's nice to just graph each function individually and then go erase parts of it. So maybe I'll try and do that as I'm doing this here. So if I'm going to graph this, let me draw. I probably should have put on some axes to start with to make things a little bit clearer, but we're just sketching a graph here, so it's okay if things don't work out perfectly. So let me investigate my domain. So we'll do kind of as I was color coding things before, we'll do x squared, and this is for all of the x values smaller than 1. So let me mark 1 on my graph here. Here's positive 1. So my output, and I'll think about maybe starting at this 1. So 1 squared is 1, so which is why I started to write that here. And if I wanted to maybe just graph the entire, let me put -1 just so I have another reference point here. If I wanted to graph this entire squared function, it would look something like this. Now, past positive 1, we're going to have to come back and erase some part of our graph here because it is defined differently depending on which part of the domain that we're in. So if we're looking at this next subdomain here from positive 1 to 2, so here's 2, what this is saying is that all of the outputs will be 3 no matter what. So let me come up, make my spacing a little bit better. There is 3. And what this is saying is that from 1, not including 1, so I'm going to put an open circle here to indicate that we're not including 1, and then everything over to positive 2 is all 3. So any number in this part of the domain here will always get sent to 3 no matter what. This is just a constant function. In general, the constant function 3 would just be everything there, even including the spot that I left blank all the way across. But we'll go through and we'll erase part of this that isn't part of what we started with, in fact. Okay, we're good there. So actually, let me just go back and I'll just get rid of that. And I will also just get rid of this part while I'm at it, just to erase that and look at just kind of piece by piece as we go. And then lastly, for any of the x values bigger than 2, what we get is just the identity function. So 3 is going to 3. Oh, I'm sorry. Yeah, 3 is going to 3. 2 is going to 2, but we're not going to include it. So I'm going to put an open circle here at 2, and then it's going to go 3 is going to 3, and we'll just kind of use not my most accurate sketch here, but should look a little something like that. Again, this isn't perfect by any means, but we are just trying to sketch a function here. So there's 2, and we're not including 2 as part of the blue identity because 2 belongs to the other part of the endpoint of this constant function. So hopefully that wasn't too confusing, but I'm really just looking at each part of the domain as we go here and then kind of sketching that. If I need to oversketch and come back and erase some parts, then that's okay there too. So there we go. We've got a piecewise function more or less sketched here. And I think with that, it's time to practice. So I wish you well. If you have any questions, please let me know, and I will see you in the next video.